All right, let's dive right in. Today, we're going to pull back the curtain on one of the most powerful technologies shaping our world. We're going to get to the heart of the engine that drives modern artificial intelligence, machine learning.
Let's kick things off with a number, 70,000. That's the number of hours on super powerful computer chips, mind you, that it takes to train just a single version of Tesla's autopilot system. That is a staggering amount of computational muscle, all aimed at one really tough goal.
Here's another one for you. 2.3 million. That is how many X-ray images a medical AI was shown, over and over, to learn how to spot abnormalities, until it got just as good and in some cases even better than human radiologists. So you've got self-driving cars, you have medical diagnostics, you have systems that predict our energy needs. These things seem totally unrelated, right? But they all share the exact same digital DNA, and that's what we're here to unpack today, this core concept of machine learning. Now, you've probably heard a bunch of terms flying around: AI, ML, deep learning. People use them interchangeably all the time, but they're not actually the same thing. So let's clear this up right now, because getting this hierarchy is really key to understanding everything else.
The easiest way to think about it is like a set of Russian nesting dolls. Artificial intelligence, or AI, is the biggest doll. It's the whole broad field of trying to make machines smart. Inside that doll, you have machine learning, which is a specific way of achieving AI. It's about letting machines learn from data. And then, inside that doll, you have deep learning, which is a very specialized, very powerful technique inside machine learning. So ML is a type of AI, and DL is a type of ML. Simple as that. So what is machine learning when you strip everything else away? Well, it's a huge shift from the old way of doing things. You see, we used to have to write out explicit, step-by-step rules for a computer for every single thing that could possibly happen. With machine learning, we just don't. We give the computer a ton of data and let it figure out the rules for itself. It actually learns from experience. Now, this is the classic kind of academic definition from computer scientist Tom Mitchell, but it's honestly perfect. Let's just break it down real quick. The task, T, is the job to be done, say, spotting spam emails. The experience, E, is all the data it learns from, so millions of emails that are already labeled spam or not spam. And the performance measure, P, is just checking how well it did, so how accurate is it at filtering your inbox. The more experience it gets, the better its performance becomes. See? It makes perfect sense.
Okay, so it turns out there isn't just one single way for a machine to learn. If you zoom out, the whole field is really broken down into three main categories, or you could say three different flavors of learning. Let's take a quick look at what they are. First up, you've got supervised learning. This is like studying for a test with a complete answer key. The machine gets tons of examples that are already labeled with the right answer. Then there's unsupervised learning. Here, there are no labels, no answer key. The machine just gets a mountain of data and has to find interesting patterns all on its own. And finally, there's reinforcement learning. This is basically learning by trial and error. Think of it like training a puppy. An agent tries things in an environment and it gets rewards or penalties for its actions. For today, we're going to zero in on the most common and probably the most intuitive type, supervised learning. I mean, this is the absolute workhorse behind so many of the apps you use every day, and it's really the best place to start if you want to have that aha moment. So in supervised learning, our data always has two really important parts. First, you have the features. These are your inputs, the different characteristics of your data. If you think of a spreadsheet, the features are just all the different columns. And then you have the target. This is the output, the one single thing you're trying to predict. This is your answer key. Now, supervised learning usually boils down to two main kinds of jobs. If the target you're trying to predict is a number on a sliding scale, like the price of a house or the temperature tomorrow, we call that regression. But if the target you're trying to predict is a specific category, like spam or not spam, cat or dog, that's called classification. Here's a perfect example of a regression problem. Imagine we're trying to predict how long a patient will stay in the hospital. The features are things like their age, gender, and diagnosis. The target we're trying to predict is the length of stay, which is a specific number, right? 3 days, 10 days, whatever. The model learns from past patients to predict this number for new ones. Now, let's contrast that with a classification example. Here, the features are things like an insurance applicant's age, their job, and whether they smoke. But look at the target. It's risk group, a specific category like group 1, group 2, or group 5. The model isn't predicting a number on a scale. It's trying to decide which bucket or which class this new customer fits into. Okay, theory is great, but how does a model actually learn to do this stuff? How does it go from seeing data to making a real prediction? Let's just demystify this whole thing by building a really, really simple classifier from scratch. Our goal? To diagnose heart disease.
All right, first things first, every student needs a textbook, right? Well, this right here is ours. This is our training data. For a bunch of patients, we have features like family history, cholesterol, and so on. And most importantly, we have the target label. We know whether or not they actually had heart disease. This is the answer key the machine is going to study.
So now our machine needs a study method. We're going to use a super simple model called a decision stump. All it does is look through all the data in the textbook and find the single best question to ask to make a good guess. And after looking at our data, it learns a very simple rule. If the patient's family history is yes, then predict heart disease. If not, predict no. That's it. That's our entire learned model. Okay, study time is over. Now it's time for the exam. Here are our test questions, a list of new patients that the model has never, ever seen before. We have all their features, but notice that heart disease column is totally blank. Our little model has to fill it in. And there you go. Here are the results. Our decision stump just went down the list and applied its one and only rule. For every single patient where family history was yes, it filled in yes for heart disease. For everyone else, it filled in no. And just like that, the machine made predictions based on what it learned from past experience. This right here, this is the core aha moment of machine learning. Now, obviously, that was a very, very simple example. Real-world machine learning is way more complex. But the crazy thing is, the fundamental idea is exactly the same. So let's just zoom back out and look at the 3 core steps that make this whole thing work. So how does the learning really happen under the hood? It's kind of like a 3-step dance. First, the machine has what's called a hypothesis space. That's just a fancy term for all the possible rules it's allowed to learn, from tiny ones like ours to incredibly complex ones. Second, for every possible rule, it calculates the risk, which is basically a score for how wrong its predictions were on the training data. And finally, optimization is the process of searching through all of those possible rules to find the one single rule that has the lowest risk, the one that makes the fewest mistakes. You know, we started this with these huge, mind-boggling numbers, 70,000 hours of training, millions of x-rays. And we ended with one tiny, simple rule about family history. But that's the magic of it all. The process is the same. It's just scaled up to an incredible degree. So I'll just leave you with this question. If one simple rule can learn to see the first signs of a disease, what happens when a machine can learn from millions of data points and master not just one rule, but millions of them, all at once?